Thank you very much, and thanks for having me here. So I have some motivation here, but we're all motivated. So let me just jump to this. I think the title of this conference goes back to this old citation that Witten once recounted, saying that string theory is part maybe of 21st century physics that has by chance fallen into the 20th century. And I want to kind of claim that maybe we can finally see what the 21st century math is. So there was a new development that roughly the 21st century, the break of the new millennium brought. And that's the development of homotopy theory to a rather new foundational theory in math. And my story today will be that I'm going to claim or present evidence that if we relook at string and M theory from the point of view of systematically of homotopy theory, that we can learn something. So there's two principles in physics that are fundamental, the gauge principle and the Pauli exclusion principle. And I just boldly claim that, or bluntly claim, that the gauge principle is, if you really think it to the end, it's what in math is represented by homotopy theory. It's the theory where you never say two things are equal. You always ask if there's a gauge transformation witnessing the equality, which in math is called a homotopy. And Pauli exclusion is in math exhibited by supergeometry, not necessarily at the beginning by supersymmetric geometry, but by supergeometry where fermionic fields are in odd degree. And we can combine that, I'll show this on the next slide, to something that deserves to be called super homotopy theory. I'm going to place us in this context of super homotopy theory, and then we just see what emerges. So there's no time here to fully explain it in full detail, but I can give you a good rough idea, I hope. So we're going to look at the local model spaces of super homotopy theory first, and then boost up a full homotopy theory from that. So the local model spaces are the simple ones that you all know. So it starts from something that's really elementary. Take the super spaces, the super Cartesian spaces, if you wish, RDN, so what most physicists would just call super space. We have to, for some geometry that we're doing later on, for doing Cartan geometry on super orbifolds, I allow myself to also add infinitesimal disks. So these super directions, as you know, can be thought of as being infinitesimal odd-graded directions. Also allow myself to have even-graded infinitesimals in there as in synthetic differential geometry. So that's some infinitesimal thickening of a point here. And finally, so the whole theory will be driven by something special happening in orbifold singularities, and I built in my generic orbifold singularity into this space of local model spaces. So this is supposed to be a point. This boldface BG is a point that is, however, a G orbifold singularity. So yeah, with some obvious definitions that I'm not stating here, the collection of these things forms a 2,1 category. And what we're going to do is we regard these things as our local model spaces and pass to a very general context of generalized spaces that are defined by the fact that they may be probed by these. So they may be much more general than these local spaces, but for each of them I know what it means to smoothly, supergeometrically probe them by these local model spaces, throw them in as coordinate systems. So this in homotopy theory is known as forming the infinity stack, infinity topos over this category of these things as a site. But it's just lots of technical jargon that just means we take the generalized spaces locally modeled on these. So that's the context where we are. And to give you some feeling for what this H is, so this boldface H, that's our super homotopy theory that I'm going to speak about. Here's some stuff that sits inside fully faithfully, super manifolds, fully faithfully embed, super orbifolds. I'm going to talk about that. They can be or can carry G structures, so the analogs of, or they can carry things like Supermanian structure, conformal structure, higher versions of spin structures, and so forth. But they also, and that's kind of the point of going to this generalized context, they also contain sort of what's sometimes called non-concrete spaces, classifying spaces, like Allenberg-Meglane spaces, but also equipped with supergeometry. So these will be classifying spaces for generalized cohomology theories with all kinds of adjectives added on, equivariant, differential. So our high gauge fields, notably the C field that we're going to discover in a moment, will be exhibited by having a classifying space here, so that both space-time, gravity, and gauge fields, high gauge fields, are unified in this context. Yeah, that's what I'm going to say about the definition of this thing. And now we're just going to going to claim some stuff that happens in here. So turns out if you go to this context, and lots of nice things happen. The first nice thing is that we discover in this blank spot here a system of what's called modal operators, of special qualities, of operations that we can, or of qualities that we can project out of each object in the superhomotopy theory. And it goes like so. So like any topo says, this global section functor to any super geometric infinity group out here. We can assign a point that gives us this functor here. And this factors in a bunch of ways. So let me walk through this. So first of all, this functor all the way down there, this inclusion of this point here has a right adjoint, and going from here down to the point and coming back is the same as choosing the initial object, the empty space in here. So the empty space is kind of discovered by this adjunction. There's also already a typo here. There's also left adjoint. If you go down and come back, right, if you go down and come back here, you find the point space. So that's rather trivial, but it's the beginning of a story. These factors, this adjoint triple that we just found, factors through the geometrically discrete infinity groupoids. So these are those spaces that have no geometry on them, but they do know about gauge transformations. So bare classifying spaces, for instance, would sit in there. This gives us an operation where we take any supergeometric infinity groupoid that we have, we just remember its underlying points and re-embed discretely. That's this operation that's called flat here that takes discrete underlying geometry. So it keeps going this way. We find continuous geometry. We find geometric realization in forms of shapes or for things. I'm not going to talk about all of these. The point is just by further factoring or observing factorizations, there's a system of operations that we discover on our superhomotopy theory, which will allow us to drive very general theory from just abstract constructions. So in particular, so we'll see this in action in a moment. In particular, the middle ones of those three operations that appear in the middle row here, which come from factoring in the middle here, they're all given by motivic A1 localizations. So So to each of them is associated a line object, such that they're given by the localization in that line object. So down here, if you go all the way down with these pi functors and then with the right adjoint back, it turns out to be the same thing as localizing at the ordinary R1 line with its smooth structure. So we're kind of contracting that line away in the sense of A1 localization as they do in motivic homology. So in some sense, this superhomotopy theory knows intrinsically about the bosonic continuum line. But as you walk up and look at these finer factorizations here, it also discovers the infinitesimal disks. And then it discovers here the superpoints. So it turns out this modal operator here that appeared here in the system, the one that comes from going down just this one step and coming back, is the superpoint. So in some precise sense, I'm just alluding to here, of course, if you just start with superhomotopy theory, the superpoint emerges by itself as a singled out object. And what we're going to do now, we apply the microscope. Since we are in homotopy theory, we can now have very close looks at objects in homotopy theory. So we have a close look at this superpoint and see what emerges out of that in turn. And I'm going to first do that in the rational approximation to homotopy. So homotopy theory is very rich. And to get our hands on it, it's often useful or often necessary to make certain approximations and start looking at certain aspects. So we look at the rational approximation and discover the fundamental super p-branes from that. Okay, here's a lot of stuff on this slide. Let me just try to walk through this. So what we're trying to do is we're trying to look at either the infinitesimal approximation to superhomotopy theory by higher Lie integration. That's essentially the kind of stuff that we just heard about from Martin. And it's actually equivalent up to some, if you're a bit careful with some boundary cases, equivalent to what in homotopy theory they call the rational homotopy theory approximation via the Sullivan construction. So consider here the category of differential graded commutative superalgebras, which is what in the supergravity literature is called category of FDAs. They call it free differential algebras. It's not really a very good name since they're not free as differential algebras, but it's an entirely standard name. Goes back to von Neuenhausen, 82. And these CGC algebras can be thought of as being the Chevalier-Allenberg algebras, the formal duals to super L-infinity algebras. So I think we've seen L-infinity algebras before. And what I'm showing here is just their algebraic incarnation. And then it turns out these sit in further adjunctions with our superhomotopy theory. So here's our full superhomotopy theory, the way just described. And it turns out if you have a FDA, or a super L-infinity algebra, you can regard it as being a certain infinitesimal super geometric infinity grouplet, namely the one that comes from Lie integration, the way we've at least implicitly seen maybe in Martin's talk. So these are Lie things that you obtain from super L-infinity algebras under Lie integration. This has an adjoint. And if we don't do this, if we follow this through to the geometrically discrete ones, then this full adjunction turns out to be the classical thing due to Sullivan, late 60s, early 70s, that approximate homotopy types bear geometrically discrete infinity groupoids by this algebraic structure. So what we're going to do now is we regard our superpoint the way we just discovered it from abstract nonsense in our homotopy theory. It actually comes under this image from the same superpoint regarded as the sort of d equals 0, n equals 1 supersymmetry, super Lie algebra. The simplest non-trivial super Lie algebra that it can write down. So I'm going to look at our superpoint now in this rational approximation, then we check what happens to it, what happens with it. So there it is, the atom of superspace, if you wish, the superpoint. It's kind of in type 1, if you wish. It has this one fermion in it. It's n equals 1, zero-dimensional superspace. It has some interesting extensions, but let me, for brevity, just jump right away to its type 2 version. So we just double the number of fermions it has. And now we're asking for the universal central extension that this has as a super Lie algebra and hence as a rational homotopy type in super geometric homotopy types. And there's some miracle that happens here. You find that this extension is R2,1/2 equipped with, so one discovers a super Lie algebra, which is the three-dimensional super Minkowski, super translation, super symmetry, super Lie algebra in Minkowski signature. So this is a little computation. It relies on the fact that Majorana fermions in 3D are given by real 2x2 matrices. And if you work out what the general super extension is, you find, since these are two fermions here, cocycles will be symmetric 2x2 matrices. So that's what makes this computation work. Then we can again double the fermions and ask next for the corresponding invariant universal central extension. Turns out this is d equals 4 n equals 1 superspace as a super Lie algebra. So this just comes from forming, if you wish, something like a Whitehead tower in homotopy theory on these super Lie algebras. So it keeps going this way, this process, which is a process that super Lie theorists would have found had they started looking at it completely independently from string theory, discovers through this iteration of doubling the fermions, forming the universal invariant central extension, it discovers all the super spacetimes of relevance in string theory. In fact, these are all the super spacetimes on which Green-Schwarz superstrings can be defined, except for the last one, which is the one where the Green-Schwarz supermembrane can be defined. But now, since we're in homotopy theory, the story doesn't end here. It turns out this space carries no further. Let's look at these spaces. These spaces carry no further invariant cocycles by which we could extend in the category of just super Lie algebras, but they do carry higher cocycles coming from the higher WZW terms of the Green-Schwarz sigma models. And since we're in homotopy theory, we can extend by higher cocycles to find higher extensions. Oh, I'm going the wrong way. So it turns out these spaces here carry extensions not by super Lie algebras, but by super Lie 2 algebras, which we call the string Lie 2 algebra, super string Lie 2 algebra. So these are super Lie algebraic incarnations of the original Green-Schwarz string construction viewed through the lens of homotopy theory. Now these spaces carry further higher co-cycles, and a whole zoo of them corresponding to all the D branes. These extensions are my idiosyncratic way of talking about what in the literature is known as the Green-Schwarz sigma models for the super D branes. But the point is that I want to emphasize is this is an entire super L infinity algebraic construction which a mathematician with no knowledge of string theory would eventually have found had you just started to classify these things. So there's
maybe you said this. Could one go along this central column? Could one keep going higher, or do things really stop in 11 dimensions from a homotopy theorist's point of view?
So that's exactly what we're doing now. It keeps going, yeah. So it turns out this space carries a 4 cycle that classifies them to, so that 4 cycle is the curvature of the W term of the what's originally called the 11-dimensional supermembrane. That's this guy. Yeah. And this carries one more co-cycle. So yeah, it keeps going, but then so it carries one more corresponding to the W term of M5 brane.
The reason why you stop doubling?
Sorry?
You have this doubling operation is the reason why you stop.
Yeah.
Oh, I stopped doubling?
Yeah.
Right, so yeah, I don't have this on this slide. One can double here once more, and then one discovers, yeah, I should put this maybe on the slide. One discovers the Haus-Weil superspace. So then the further extension, so if you double once more and further extend, you get a small sector, a very small sector of OSP 32/1, namely the sector that contains R10, it contains one 32 and the other 32 and the dilatation operator. And then it stops in the sense that then you still double because that extension doesn't change the doubling, and so there's no further extension. Yeah, I should have drawn this here. So there's one exotic corner where you go almost 12D, but not quite. But let's not get into this now. And then these are the higher co-cycles, and they stop here. There's no further extension.
It does truncate at some point.
It does truncate here. Yeah, after branching out into this kind of mysterious 12D region. Yeah. But then it's just stop. So the process, so the mystery, or what makes it stop is that we double here, we go to n equals 2 in 11D, which one can do, and then from the extension, that extension is still n equals 2, because the space-time dimension doesn't increase. It just picks up this conformal factor, so it remains 32 plus 32. And so if you now say, let's go to the double, you discover, well, we already doubled, so and there's no further co-cycle, so it stops. So yeah, I think that's maybe a modern reason or a good mathematical reason to really stop here. The folklore likes to stop here just by counting. They go back with double dimensional reduction to d equals 4 and say, oh, we don't want spins of greater than 2. It's a bit of a vague argument, but here this process actually stops. Yeah. Okay, so I want to focus. So there are lots of things to be said here. Yeah, we worked out some things. There's you find at this rational level, you find everything that should be there in M theory. There's M2A duality by some homotopical double dimensional reduction. One can find gauge enhancement that, yeah. One can also go further here and not just double, but go all the way to, keep doubling to find the exceptional superpoint. That invariant extension gives exceptional super space-time. And there's stuff that can be found there. But I want to focus now on, we want to get M theory to work here, so let's focus on this M-brane part. So just to summarize, somehow by some systematic math process, we went from the superpoint to M-branes. Let me give you more details on what this M-brane piece up there actually is, to show you that this is stuff that connects to known things. So I'm claiming here this is the super Lie algebra, the supersymmetry super Lie algebra in 11D, just the translational part. And I'm claiming it has this higher extension here. What is it? Well, it's the thing that's classified by a 4 co-cycle, which I call mu M2. And that co-cycle is just what in the literature you find as DLWZW. It's the WZW term of the M2 brane, written in the usual notation, which I haven't introduced here. So these are field-bound fields. These are the left invariant super 1 forms on the corresponding super Lie group here. So there's this 2 gerb, if you wish, that is classified by this 4 co-cycle, and this is the rational version of the M2, of the C field 2 gerb, if you wish, on super space-time. Similarly, there's this co-cycle here, a 7 co-cycle on this M2 brane extension itself, and that is just what in the literature you find as the WZW term of the M5 brane, the Green-Schwarz type M5 brane. So, but let's unify them. Turns out there's an analogous homotopy fiber sequence here that pertains to the coefficients. Oh yeah, I should say so. So this 7 co-cycle here, rationally, so you would think it goes to B7R, it's a 7 co-cycle, but rationally there's no difference between B7R, the Einberg-MacLane space, and the 7th sphere. And if we do write the 7th sphere here, it kind of simplifies understanding what this homotopy fiber sequence is. Namely, you can put the rational 4 sphere here, and then this fiber sequence is the quaternary Hopf vibration in its rational incarnation. And the thing is that, so there's a general theory about descending super co-cycles on sort of total spaces of homotopy fibers down. Well, you have to ask for a factorization here that makes this commute up to homotopy, and this turns out to exist. So this stuff we did in 2015. Hisham and Domenico Fiorenza. So it turns out you can kind of unify the M2 and the M5, not kind of, they are unified by a co-cycle that goes right here to the rational 4 sphere. So what does that mean? Let's unwind this in components. So I'm claiming that what this process really discovered is a co-cycle in rational cohomotopy, as it's called, a map to the rational 4 sphere from super space-time. So that cohomology theory where you map to the 4 sphere is called cohomotopy. And that co-cycle is just the following thing. So the rational 4 sphere is characterized by its by two form components. There's the G4 flux and the G7 flux kind of in the universal incarnation as being elements in the Sullivan model for the 4 sphere here. And that co-cycle sends the G4 flux to the bifermionic component that it always must have in 11-dimensional supergravity. And it sends the 7 flux to the corresponding bifermionic components. So these were previously, you can recognize them, they were the ingredients of these Green-Schwarz co-cycles for the M2 and the M5 brane. And now Sullivan tells us, or told us way back, that the rational model of the 4 sphere in this algebraic incarnation is given, it has these 2 generators and they satisfy this relation. The G4 is closed, G7 is not closed, but D of G7 is up to a factor, G4 by G4. Now, these relations, which are purely math here, this is just a model for the 4 sphere. They are, of course, the equations of motion of the C field in 11-dimensional supergravity, where if you, yes?
Question again. There's another equation, which is G7 is star G4.
Yeah, so that's...
Does that come out anywhere?
It will, yeah. Not at this point yet. At this point, we're just seeing kind of the cohomological nature of these things, the equations of motion, which make them self-dual. So there's no metric at the moment, but it will come. It will come. Once the metric is there, it forces them on shell and makes them Hodge duals of each other. But at the moment, we're seeing, just like you can discuss RR charges, first of sort of just cohomologically, you just say it's a self-dual co-cycle in, it's a co-cycle in, or self-dual co-cycle in twisted K theory, and then you impose the metric condition that makes the duality be given by the Hodge star. So at the moment, it's just cohomology. There's no metric yet. The geometry will come as we do more, yeah?
Why do you start with superpoints and not superlines or superpoints?
Not superlines? Well, but they emerge out of the superpoint. So I didn't give the extension out of the superpoint. So the universal extension of R01 itself before we double is actually R11, the superline. How do you do ones? Universal central extension. So this is, if you wish, supersymmetric quantum mechanics that sits here. And then we started the process that we said, OK. So I'm starting from the simplest object that was kind of God-given to me by superhomotopy theory. Superhomotopy theory kind of discovered this thing, said, look, it's there, you should study it. And so then we're studying this. And then we found Super-Minkowski. You know, I don't want to, sorry, to this. See, part of the game is that I want to put stuff by hand. I don't want to say, I want to study the superline, but I just want to see what develops out of this homotopy theory. Ah. Oh, then double again here? Yeah. So there's no, there's... Right, you can, there's parallel process. Yeah, there's nothing interesting that comes further out of this. So maybe to go back. So this process, I'm not showing everything you can do. Like this whole sequence of stuffs you can do here. You can have n equals, 1 to 32 of the superpoint and consider the extensions there. We haven't studied all of them, so I'm giving you this. I'm giving you a glimpse of this here. But there's room to study the intermediate extensions here. I think they will come from intermediate exceptional geometry. So this is like the full M-theoretic exceptional geometry. And I think this gives the intermediate piece, but we haven't done that.
What he's asking is that it's like 1R1/1/1. If you get the same kind of sequence about, different starting point, you get a different sort of.
So you start with R11, you double your Furman, as you did for R01.
Yes.
Or you start with
Yeah, I'm saying then it already stops. There's no further interesting cocycle there. There's no further invariant cocycle after this. So this just produces the superline and then stops already. This produces the usual picture of M theory and then stops. This produces the exceptional picture, and then we're not really, I know only a little bit of this, and then in between here, all this needs investigation. Let me head on, there's stuff to be told. So just to amplify here, so this was Hisham's original observation in 2013, that the equation of motion of the supergravity C field is actually is the rational force sphere. And we're beginning to see more and more that this is more, so Hisham suggested back then that this should mean actually that we should regard membrane charges being in cohomotopy. By this analogy, so we've worked this out a bit more, so there's, so this is our article with Vincent here. So there's a lot of hidden in this little line here, but there's a way to implement double-dimensional reduction, gauge enhancement. We can see all this on the super infinity algebra thing, and it turns this sphere-valued cocycle into, on the rational level, into the sort of familiar twisted K-theory valued cocycle of the D-branes. So there would be lots to be said about this, but here I just want to make this punchline that just by analyzing the super L infinity geometry, one finds from first principles, without us putting any wish list in by hand, that there is the following analogy. It's just there. So the same way that the D-branes have charges in twisted K-theory, on the rational level, that's exactly how the M-branes, what we just discovered, have their charges in cohomotopy in degree 4. So the question is now, is this... Oh, sorry.
Now it's my turn to echo Jacques' question. So you can also get D-branes from M theory by looking at KK6 monopoles or KK1.
Yeah, you get some of the black branes.
How does that fit in?
It comes from the Equivariant enhancement. So maybe I don't have a slide for that. So what I'm discovering here are the fundamental D-branes. These are. So I'm making this distinction between the Green-Schwarz sigma models for branes and the black branes that arise at singularities in supergravity. What I'm discovering here at the moment are the Green-Schwarz terms for the fundamental sigma model D-branes.
But once you go to 10 dimensions, you can't distinguish them, because you can, KK6 and degree 5.
Well, they're still distinct. One is a black brane is a solution to supergravity, and a Green-Schwarz brane is a sigma model. They're not the same thing mathematically. There's a very close relation. No, these are, no, this.
If you take an M5,
Yes.
right, or a KK6,
Yes.
you can get objects that are T2.
Yes. So, yeah. So I don't have slides on the black branes now, I think. But so what we're going to do is, so we have these fundamental brane cocycles, given the Green-Schwarz sigma models, we will regard them in equivariant cohomotopy. The equivariant cohomotopy will make orbifold singularities appear on the spacetimes, and then we see that equivariant cocycles and equivariant cohomotopy unify kind of the branes in their sigma model incarnation with the branes as their black brane incarnation, what you're asking for. Yeah.
Rationally, it's hard to tell the difference between K-theory and cohomology.
Right, but it's easier to tell the difference.
In fact, there really isn't a difference.
There is a difference.
Only over the integers that these theories differ. So, if I never heard of that the D-brane charge was quantized in K-theory, I would have been happy hearing that I discovered cohomology or twisted cohomology through this story. Rationally, over the integers, there's a difference, but you're
Absolutely.
rational.
Absolutely. Up to now. So we're going to boost. We're going to boost. I just want to amplify that actually in the twisted K theory is also rationally distinguished already from twisted cohomology. The twist makes a difference here. But it's true that this cocycle comes down to just, in quotation marks, being a twisted de Rham class on the super spacetime, yeah. But I'm just saying, at the rational level, where at which I'm at the moment, these are just completely parallel. But for both of them, we should now ask, what is their lift beyond the rational approximation? That's exactly what I'm going to do now. So we have this. So there's, in general, many possible lifts of a given rational approximation to a non-rational full thing. So let's think about what we can do for a cohomotopy. There's one lift that is minimal in the technical sense that it consists of the minimal number of cells, if you think of CW complexes in homotopy theory. And there's just the actual force sphere. So this was represented by the rational force sphere. And one obvious choice one can make here is put the actual force sphere. So what I'm going to do now, I'm going to make a hypothesis. I'm going to say, OK, let's check what happens if we assume that the formalism is trying to tell us we should take the actual force sphere here. What kind of theory do we obtain? So that's the plan now here. So we discovered that M-brane charges is rationally in cohomotopy. So I'm going to construct now the differential equivariant full refinement of that, which will go by this name, head S4. And then we're going to impose the condition, it's kind of an equation of motion, that the underlying four forms of these are in each tangent space. This is a picture of Minkowski space, the given cocycle that we just saw. But globally, it's some map to the force sphere or the equivariant force sphere. And the fact that it's equivariant will make orbifold singularities appear, which will be interpreted, or will have as interpretation, being the black branes. So there's such a theory one can develop. And then in the last step, and I won't have time today for this, one can then take this and compare it to various corners of M theory and check if it's right. OK, so let's bring in those orbifold singularities here. So this, mathematicians call this global equivariant superhomotopy theory. For us, or for physicists, this will be bringing orbifolds into the game. So here's a bit of abstract nonsense again. Just bear with me. It's just to indicate that just from putting on a category theorist's hat and just analyzing the situation we're in, we discover three more of these modal operators actually here. So it turns out we can factor the whole thing. So remember, this was our decomposition we started with, or we found at the beginning. It turns out this actually appears twice, kind of once with orbifold singularities and once without, exhibited by certain factorizations. In any case, our supergeometric infinity groupoids here can now be, we can request of them to reveal their singular aspect, their smooth aspect, and the orbi singular aspect by going through these functors here in various ways. So the difference between singular and orbi singular, as my notation is supposed to suggest, is here you just take an orbifold singularity just as a naive quotient, whereas here you remember that there's something interesting happening there, possibly at the orbifold singularity. So it's this orbi singular aspect that will bring equivariant cohomotopy theory into the game, which will kind of serve as our microscope to look inside the orbifold singularities and discover the hidden degrees of freedom there. All right, so using this, now it becomes a bit more abstract. Just bear with me for a second, or for how long it lasts. If you ever looked at the literature a bit beyond the global orbifolds that are usually considered or discussed in string theory, if we really now go serious and say the full curved space-time should be one huge orbifold with many different singularities, then we need a good mathematical definition of what an orbifold actually is. Of course, we're not the first to ask this question, but it turns out, despite the simple idea, there's some subtleties involved in the definition. And there was actually, up to recently, or maybe up to now, there was no real definition of orbifolds in such a way that the cohomology would actually reproduce equivariant cohomology as opposed to just cohomology with twisted local coefficients. So I'm not going to go through this here. The point is just that in this abstract context that we're in, the superhomotopy theory, using all these modal operators that we had, orbifold singularity, this infinitesimal shape, and these things, there's a simple definition one can give now that tells us what is a G-orbi V-fold. So I'm just pick any local model space V on which this thing is supposed to be modeled, and I prescribe some finite group inside which all the orbifold singularities should happen. And then I can say this. Here's an example that will guide us now. So we're interested in the force sphere. So the force sphere, so what is it acted on? So we need to put everything in the context of spaces with actions now. So the force field is acted on by O5, of course. Actually, I'm going to have pin 5 act on it. And see, this flat sign here means flat was take the discrete part. So this means I regard pin 5 as a discrete group. I forget its smooth structure. And then pin 5 unifies two kinds of singularities that we need to see. So inside there is spin 4 and an orientation reflection. The spin 4, in turn, is the product of two copies of SU2. And that's two copies of ADE singularities that can appear.
Pin 5 plus or pin 5 minus?
Yeah.
Two different pin groups.
Yeah, I guess we want to, I guess plus. So we need this thing in there, right? Yeah. And then there's also this reflection on one of the directions, which is orientation reversing and will serve as parametrizing the O-plane singularities. So if we write the boldface S4 as being the incarnation of S4 as a smooth manifold embedded as such into our superhomotopy theory, then we can form this homotopy quotient by this discrete group, pin 5, and regard, that's what this little symbol now says, project out its orbisingular part. So regard the thing as an orbifold. And we can take its shape, so it's geometric realization. So this is just the force field as a homotopy type with its same action. So these things exist now in this context. And now I can say, what is equivariant cohomotopy of some super orbifold? So my local model space is going to be, right, since this is what we moved up in our rational story. So I take the tip of that story, that was the 11-dimensional Superminkowski spacetime. I regard it as a group object via, as the translational supersymmetry group in 11D, and pick any super orbifold locally modeled on this as on the previous slide. Then I can now say what is the equivariant cohomotopy of that orbifold. It's just HOMS, the HOM space in my homotopy theory from X, sort of regarded in that slice, mapping to S4. And by the magic of superhomotopy theory, this diagram now encodes all the equivariant structure that you may want to put on at the singularities of that orbifold on your cohomotopy theory. So the given cohomology set is then the connected components of this. But we need a bit more. We want to bring, so this would be, what we just said would be the topological part of the charge quantization of our C field. We want to bring in the differential forms. So I'm going to just briefly indicate the differential refinement of this to differential equivariant cohomotopy. For that, we need this object, which is the classifying space, if you wish, a sheaf, of course, of flat superforms with values in our equivariant force sphere. So as a sheaf, it's the object in our superhomotopy theory which to a super space-time and the orbifold singularity labeled K, some embedding into pin 5, assigns, so this is supposed to be read as the space of flat superdifferential forms on our super space-time with coefficients in the L-infinity algebra that corresponds to the minimal Sullivan model of the K fixed points of that force sphere. So if K is the trivial group, it means we're not at a singularity, then this is just the L-infinity algebra such that flat forms are just those that we've seen before, pairs of a 4 form and a 7 form satisfying the equations of motion of supergravity. But in order to make this equivariant, there's this fixed point thing going on. So then one can form the shape, the geometric realization of this. This turns out to be the rationalization of the force sphere. And this allows us to do the following construction, which is, if you wish, the unstable generalization. We're not working with spectra here. The unstable generalization of the Hopkins-Singer construction of differential cohomology theory. So we take the fiber product of our equivariant force sphere with those differential forms over the rationalization, meaning that this part measures some topological part, this part measures the form part, and we say in here, as rational cocycles or as realified cocycles, they need to coincide up to homotopy. So that's the usual way that you glue the curvature forms to the topological data by local gauge transformations which encode the actual connection data. And hence, we can now say differential equivariant cohomotopy on our super orbifolds as the connected components of that space of maps into this new object in our superhomotopy theory. So, this is just so one has to unwind now and work on. This is what we can do now. You have to unwind what this is, but the point here is that this does now have a good definition in the superhomotopy theory. So just to amplify what we constructed here, this is by analogy. Here's the C field or our proposal, right, for the charge quantization of the C field, and this is just by analogy to compare it to the old Dirac charge quantization of just the A field, the electromagnetic field. So we have now differential forms being represented as maps from our orbifold to this sheaf of flat forms. So this will encode pairs of flux forms for M theory. And on the right, this corresponds to picking a Faraday tensor written here in this funny Yoneda kind of way as a map from space-time into the universal sheaf of flat forms, in this case, closed two forms. And then we can say, just like Dirac said in modern language, that the charge quantization for the Faraday tensor should really mean that you lift this map to, so this is my funny notation for ordinary differential cohomology for line bundles with connection. So you have to choose a line bundle with connection whose curvature is this F2. And now we have, instead of line bundles with connections, we have this differential cohomology theory of the force sphere, the equivariant force sphere. But we can again play the same game. We say now a charged quantized C field is a lift of this map here. So that would be a reasonable candidate now for a non-rational lift, beyond rational lift of our simple rational cohomotopy that we discovered from rational superhomotopy theory. Now, finally, maybe I have 5 minutes left to bring in the equations of motion. For that, we need to bring in geometry. We can also do this here. So we haven't used all of our modalities yet. So let's use some more. So the principle of equivalence, maybe in its best mathematical incarnation, is really what is encoded by Cartan geometry, right? So as you all know, spacetime should be locally equivalent to Minkowski spacetime, and one needs to say, well, in which way do we mean this? So it should be that on infinitesimal neighborhoods of every point, spacetime should be equivalent to the corresponding infinitesimal neighborhood of super Minkowski spacetime with whatever extra structure we want on that. So here's a cartoon of that where you see some curved spacetime. It's still pretty simple. It has these infinitesimal neighborhoods here, and the super field bind is really the identification of that with a piece of super Minkowski spacetime. So that's the idea. What we need to do is we need to formalize this and give it a math home. Okay, so that's maybe a technical slide. It shouldn't be so technical towards the end of a talk. The punchline is just that using our modalities, we can say these things. So you see this is this infinitesimal shape here. So first of all, given any local model space V, it turns out you can speak about its infinitesimal disk around a given point by forming some homotopy fiber product over this de Rham-State constriction. And then there is canonical ways of saying what it means to have a G structure on our orbifold, on our super orbifold. Well, first of all, one has to prove that every Orbi V fold carries a canonical frame bundle. It takes a bit of work, but it just follows from the general theory. And then we can lift that frame bundle to a G principal bundle. And it turns out that V itself, the local model space, always carries a canonical such G. So that's why it's called E. This is the generalization of a field bind, right? If you put in G, something like the orthogonal group, this encodes matrix structure. If you put in something like symplectic groups, this encodes symplectic structures and so forth. The local model space always carries a canonical G structure given by left translation, since it's a group object. And so we can ask that our G structure is that also the G structure is locally that of our model space, well, by requiring that on infinitesimal disks, the G structure on our X coincides with the canonical one. There's some choice here how big you make your formal disk. If the infinitesimal disk is first order, then you would just call this torsion-free. If it becomes infinitesimal order, it's torsion-free and flat. Anyway, we can say these things now. They're all there. And now we can bring in the equations of motion. So our choice for V is that 11 is super Minkowski spacetime regarded as a supergroup translating over itself. And so let X be some Orbi fold locally modeled on D equals 11, N equals 1 supersymmetry. So then here's a list of claims. So there's a canonical group that we can actually ask to reduce to. It's just the automorphisms, the bosonic part. So this arrow is for bosonic part. The bosonic part of the group automorphisms of this thing turns out to be the 10-dimensional spin group. So then we can ask for a G structure on our super orbifold. Well, if everything I've claimed so far makes any sense, well, this should be the usual notion of geometric spin structure now on, lifting our GL 10,1 structure. And so that does encode a field bind and hence a metric field of gravity. Still off shell. So now we can ask that on infinitesimal neighborhoods of any disk that actually coincides with the canonical left invariant such G structure. So since this is a field bind here, you can maybe easily believe that the standard superfield binomial Minkowski spacetime, which we've briefly seen before, encodes such a structure if we let X be V. So we can now ask that our geometric structure on the superspacetime is infinitesimally equivalent to that. And by a remarkable theorem of Candiello, Lechner, and Howe from before the 21st century, actually, it turns out that just requiring the supertorsion on a 11D superspacetime to vanish is already equivalent to the equation of motion of 11-dimensional supergravity. The supertorsion. So in the supertorsion, that gamma matrix goes to the left side. So we're on a non-abelian group manifold, so the supertorsion tau is dE plus psi bar. So that's the thing here. So we're locally modeling our spacetime on the supertranslation Lie algebra. The supertranslation Lie algebra is actually a non-abelian group. This is something that's maybe not highlighted very much, even though it's very elementary. Supergeometry for supersymmetry is actually slightly non-abelian in that you're modeling on a non-abelian group, and that gives this extra term. And so asking the supertorsion to vanish is asking the ordinary torsion to be equal to that gamma matrix. Yeah, and that, yeah. So that's a statement by Candiello and Lechner and Howe, which I think needs much more prominence. I think it's pointing to something deep, and here it's our connection between the abstract math and the actual supergravity. The abstract math gives us a handle on saying torsion-free G structures in grand generality. If we do it in this case, am I still pointing the right way? That turns out to be put our theory on shell. And now we don't have to do the next thing, but the math suggests it. Actually, we want to do this on the infinitesimal disk, not just the first order disk. That makes the G structure flat. That makes this orbifold a flat super orbifold, so it puts now another constraint. And here's a funny typo. So that really means now that we're on an orbifold where all the curvature is concentrated in the singularities and all the flux. And I think, yeah, so one can consider this. And then consider effective curvature given by some guess of orbifold singularities. And the good thing about it is that, so it's unknown currently, right, what the higher curvature corrections to 11-dimensional supergravity are and what the higher analogs of the G flux quantization condition is. But since they're now all cramped into the singularities, and my theory knows about some secret degrees of freedom sitting at the singularities given by equivariance, the theory knows how to deal with it somehow. Okay, so in conclusion, here's the proposal for the non-rational lift of this cohomotopy M-brane charge that we found. We can consider the following thing. We define the covariant phase space of some M-brane charge enhanced 11-dimensional supergravity as being this funny fiber product. So so this just to say that we can make this mathematically precise, but let's just unwind what it means intuitively. So we say the full covariant phase space of our theory, some M enhancement of supergravity, is the following. So for each class of superorbifolds, with the corresponding, so they're locally modeled on D equals 11 and equals 1 supersymmetry, and I require the singularities to be in pin 5, so for each such class, here's the field of gravity in brave new language. It's a spin 10,1 structure on the smooth part of my orbifold, which I can realize, remember, it was a slice construction, and this says that torsion vanishes. So this is newspeak for just on-shell 11-dimensional supergravity. Out of that, I can project out the corresponding four-sphere value it forms, the G-flux. And this fiber product now says that whatever I'll put here is supposed to lift these corresponding four forms. Namely, what we have on the other side is now this lift differential equivariant cohomotopy of this form flux. So this is something one can now define and study. We can now define the space of observables on this break new phase space. And since we're in homotopy theory, we should, instead of saying R-valued observables, we should say the differential HR cohomology, equivariant of this covariant phase space. And now this is something one can analyze and try to check. So this is a space of observables, so we can check, does this have anything to do with M theory? So I'm out of time now, but I just want to indicate that we did some checks. and that it looks plausible. So this is the stuff I just talked about. This is 11-dimensional supergravity with M-charge enhancement. So now we can look at now various different sectors of this very rich space of observables. First, we can forget all the topology. We have this fiber product. Just forget one side of it. Just remember the differential form data, but it's equivariant now. Oh, sorry, no, I'm talking about here. Just consider the differential form data, and yeah, we get again what I already showed, this relation to rational twisted K theory. It's still in here. We can keep the equivariant, stick to the differential forms, but make them equivariant. Maybe I should have shown slides for this since there was some interest here, but maybe I can do this later in the coffee breaks. So this turns out to reproduce the black M branes locally in Super-Minkowski spacetime as orbifold singularities, gives the right classifications. And it also recovers, interestingly, the full Green-Schwarz action functionals for these branes in the super-embedding formalism. Remember, we just started actually with just the WZW terms. I never talked about the kinetic term. It turns out to come here. It turns out to come from this equivariant enhancement. Yeah, this here. So, so one can, I think I'm out of time. One can map to fractional d-brane charges, to fractional M5 brane charges, and see that things work. I think I'm out of time. I should stop here. I would have, if there's interest, I can say more, but let's stop here.
Questions for Urs?
I'm not even quite sure how to formulate this question, but is there any way to see that if you take this 11-dimensional, this pin 5 structure that you had to impose? So what we found, when you reduce to some 10-dimensional theory, and so we're talking about ordinary orientals, there's something that we in our work called a twisted spin structure. And there are topological conditions, for instance, for the existence of a twisted spin structure. Do you see that your pin 5 structure reduces to that in any cases?
Right. Yeah. So I haven't. So I can't say I have studied that in detail, but I just want to amplify that by the general logic of M to A duality, it should be. So this pin 5 structure was there to unify the ADE singularities and the O planes up in 11D.
Well, I mean, so our story was, again, rather general in 10 dimensions. Any group action could even be trivial on the spacetime with a Z2 subgroup that is accompanied by orientation reversal on the world sheet. That required part of the data of a string background was this thing we call a twisted spin structure. Yes. And for instance, there are topological restrictions on your spacetime.
Yes.
In order for it to emit such a thing, and it would be interesting to see whether
Yes.
This story reduces to that when you reduce from 11 down to 10 dimensions.
Absolutely. Yeah.
I'm pretty sure that story is right.
Yeah. Absolutely. That
That's a good
gets to
thing
be
to check.
checked. Yeah.
Okay. Excellent. Other questions for Urs? Martin.
So when you do take the carry-off prime and high string corrections
Yes.
into account, then you know that the super torsion won't vanish. It will be deformed.
Yeah. So you see, so the picture here is, so if the super torsion, you see, when we say flat orbifold or super torsion free orbifold, it really means away from the singularities. So that's exactly the picture now, right? So we have these spaces now that are flat everywhere and vanishing torsion everywhere, except at the singularities, which we shrink kind of to zero size, because they're really just orbifold singularities in the end, right? So we got a picture here where I try to indicate this in one of the slides, where we form a curved supergravity space-time by a guess of singularities locally, it's always flat and super torsion free, away from the singularities, and then all the flux and all the curvature is sitting in the singularities.
So you say basically that, yes, there are higher order
Yes.
and so on, but we're just going to assume they all vanish except at the singularity.
Well, they certainly vanish here because it's flat here.
But why should it be flat?
It's flat by decree. We're looking at those spacetimes.
Okay.
Yeah, we're looking at those spacetimes that are piecewise flat, except for all these orbifold singularities. Then we apply our magic magnifying glass to see what happens. So this orbifold singularity you should think of, or you may think of as being the limit, where your ADS throat geometry really collapses to, right? You're in the far horizon limit. So it's all inside here now. So what is happening inside there? Well, how does our formalism know? Well, in here, there's some equivariance happening here. So the whole business of setting up the theory of equivariant cohomotopy on orbifolds is to make precise what it means to equivariant cohomotopy theory around these orbifold singularities. So some extra stuff happens here, encoded in this enhancement of our C-field cocycle to a cocycle in equivariant cohomotopy. And that is the extra structure that will know about all these brainy effects. So for instance, when we map from equivariant cohomotopy to K-theory at the singularities, we will get this map from this equivariant cohomotopy equivariant K-theory, and we see exactly how this equivariance degrees of freedom gives us fractional d-brane charges, d-brane stuck there. So that's the picture here.
I still don't quite understand how it will tell you about higher curvature terms.
You see, on a flat orbifold, you can think of the curvature as being delta distributed on a bunch of points.
How do you distinguish R to the 4, R to the 8, R to the 6, R to the 8 terms?
Yeah, I don't distinguish them. There's somehow, I mean, I'm just setting up a theory that knows how to deal with these infinite curvature singularities. So the theory now knows what happens with infinite curvature at these points. It's all encoded in the fact that it knows, well, if there's infinite curvature here, it's an orbifold singularity, so I need a theory that knows about what orbifold singularities are.
Do you have any evidence that such a theory exists that can take into account all the infinite alpha prime and G-string corrections? One linked exam theory?
Yeah, I mean, that's the claim. So we've set up the theory, and now we can, so the theory is set up, a candidate for that, and now I can look at various of its corners, and so far all the corners we checked do look right. So there's, of course, many more corners to be explored, yeah.
For example, Mike Green and collaborators have written down proposals, concrete proposals for things in 11 dimensions. Can you see those in your work?
For the higher curvature terms?
Yeah.
Yeah, of course.
It allows for them, but there's no systematic way of spitting them out explicitly, but it allows for them.
You see, what they write down only works for a smooth geometry.
Sure.
So they don't know what it means to have these high curvature corrections in orbifold singularities. So,
You could relax your assumption that the rest of your space-time is flat, study curve backgrounds, and then we could
Take the limit.
I mean, I think Martin's question is really only well posed on the smooth part of your space-time.
exactly, yeah.
Right,
You can't take the limit.
Well, first, let's answer it on the smooth part of your space-time, then we can worry about trying to take a limit. Right? I mean, as you say, the limit is going to collapse all sorts of things on top of each other, so if we haven't straightened them out in the smooth case, we're not going to know how to do it.
You might worry it becomes too singular and have ill-defined products of distribution.
Yeah, you might worry that such a theory cannot be set up, and so it can. But yeah, of course it needs further checking in comparison to all kinds of other things that have been done. There's 24 hours in a day, and we're working on it.
Other questions for Urs? Okay, let's thank him again.
So maybe we'll come back now. It's 4:10.